In this tutorial, we're going to finish up our discussion of the basics of universal gravitation by introducing a fairly abstract concept, something we'll talk much more about in year 2, and it's the idea of a force field. All right, in this particular case, we're going to look at a gravitational field, and we're going to introduce a new term that's related to force but is not the same as force, and that's called a field intensity. Okay, and it turns out our field intensity is nothing more than our old friend little g. Little g is usually thought of as the acceleration due to gravity, and it is when an object's falling, but there's another way to interpret it completely independent of the acceleration due to gravity, and that is as an intensity. So I'm going to try to give you a kind of a very broad idea of what a field is and what intensity is before we get into mathematics. So I'm going to turn to a different spread page here and try to give you an idea. So let's say this circle represents a planet, and let's say in this case the Earth. Okay, so if there is another planet out there, or a moon, or whatever, we know there's going to be a gravitational attraction between them. And a question arises, well, how does this object, let's just call it little m, communicate to the Earth that they're pulling on each other? Okay, so Newton was never able to answer that. He just was able to model the magnitude and direction of that force. About a few centuries later, the idea of force fields became or developed and became in fashion, and they offered well, you decide whether it's an elegant solution or somewhat artificial. And what they're basically said is what's in contact between the planets is a force field. Okay, so surrounding the Earth is a field. It's like an aura that spreads out in all directions out to infinity, that's communicating, hey, I'm going to exert a gravitational force on you if you have mass. And so what we can do is represent that field with field lines. So what we would do, and I'm not going to go into the details of why the field lines look like that beyond the obvious, we'll eventually talk about that when we talk about other forces, is that we can pretend that the Earth is surrounded by these field lines, and what you can see is the outstanding attribute of these field lines is that they are directed inward towards the Earth. So this object M would be pulled in towards the Earth because it's in the presence of that field. So let's say the field line doesn't stop at the mass, it goes out to infinity, and that's not really the issue here. But this mass feels that force field, it's in contact with that, and so it's going to accelerate inward towards the Earth. And we can make an argument that this little mass has its own field, but we're going to pretend that it doesn't exist for right now, for reasons that will become maybe a little bit clearer in a minute. So what we want to define then is a quantity that depends on the Earth and the Earth only. And that can't be force, because if we try to define the force of gravity, well, that depends on both masses, right? The mass of the Earth and that little m. So I don't want that. We want to define the strength of the field based on the Earth. And there's two things that go into that strength. How big the Earth is, right? The more massive an object, it will make sense, the more or stronger the field's going to be. Less obvious, but should make sense, is where you are in the field. So if the little m is right here, it's going to feel a certain strength. If it were right here, we'd expect the field intensity to be stronger, simply because you're closer to the Earth. It's kind of similar with an aura may surround a person, right? A certain person might exude a certain confidence, let's say. Okay, and how much confidence you pick up, A, depends on the person, and B, maybe your proximity to them. The closer you are, the more confidence you might gain. The sense further away you are, it might get a weak one. I don't know, that's not the best analogy, but I imagine you can think of other attributes that people might have that are not tangible, but you gotta, a feel for them about that. Okay, so let's go back to the definition then. So the definition of gravitational field intensity is actually very simple, deceptively simple, and often misleading for kids. Okay, it's simply a ratio. Okay, it's the ratio of gravitational force to the gravitational mass of an object. All right, and someday I'll teach you about the difference between gravitational mass and inertial mass, but that's I don't want to go into discussion now. So the symbol for gravitational field intensity, which I sometimes call GFI, is little g. And if we base it on the definition, it's nothing more than f of g divided by m. If you look closely at that equation, that lists nothing really more than, if we rearrange it, Fg equals mg. Okay, so they go hand in hand, but this is defining the field intensity based on the force between two objects and the mass of one of those objects, generally the smaller object, if you will. So we can expand this equation. So I'm going to just do a little work up on the side margins here. F of g is really big G, mass of one object divided by the mass of another object divided by the distance squared. And if I take this mass, well, let's call that just one of the objects. We see that the mass cancels out. So the most generic way of calculating little g, the gravitational field intensity surrounding a planet, is take big G, the universal gravitational constant, times the mass of the planet in question, and divided by how far away you are, or some object is, from that squared. Okay, so to go from this equation is a fairly simple derivation, and you want to be able to do that. Okay, so here is a picture over here of what I was trying to represent on the other page. This is showing what the field looks like surrounding the Earth. The key things is that the field lines all point towards the center of the Earth, because anything placed in a field will fall in. But a very, very important attribute of the field, little g, is it does not depend on this. Okay, it does not depend on the mass of the object in the field. Now, it might look like that in the equation, but you got to remember, in the numerator is hidden the little m as well. So it always cancels out. So this, if you want to understand what factors affect the intensity, this is the equation you want to look at, not the definition. I know it's confusing, but with practice, it'll start to make a little more sense. Okay, so let's say you've got some mysterious planet X, has a mass, right, and a certain size, and we want to know what is the gravitational field intensity, little g, at the distance from the planet. How strong is the field? Well, we have two choices. We have this equation, based on what we know. We know the mass of the planet, we know the distance, and so it's going to be the second one. We would say little g is big G, mass of the planet, I'm just going to leave it as a big M, over r squared. Okay, 6.67 times 10 to the negative 11th, I'm not going to put units here, times 6.0 times 10 to the 24th, divided by 6.36 times 10 to the 6th quantity squared. All right, if you plug in the numbers, make sure you use your EE button, you will get about 9.8. And if I look at the units, it's a little bit difficult to get the units from here, but I can look at the definition. It's got to be newtons per kilogram. Okay? Now, it's not a coincidence, this 9.8. All right? These are the parameters of the planet Earth. This is the mass of the Earth. This is the Earth's radius. So when you're standing on the surface of the Earth, the gravitational field intensity you feel is 9.8 newtons per kilogram. So there's your derivation of why little g is 9.8 for the Earth. It's simply based on Earth's mass and its radius. Now, what's the use of knowing that the gravitational field intensity is 9.8? And again, we're not talking about an acceleration. Well, we could ask, how much would a 50 kilogram object weigh at this point in the field? So if we were to place an object right here near the surface of the Earth, we can ask, what's the force on it? So that's where we use this equation. In other words, if little g, by definition, is f of g divided by the mass of the object in the field, not the mass of the object creating the field, then it follows that the force of gravity is nothing more than m times the field intensity. So when you look at g as newtons per kilogram, the field intensity part makes a whole lot more sense. So we'd say we got 50 kilograms in a field that is 9.8 newtons per kilogram. So that's a constant for the surface of the Earth, and that would give us 490 newtons. Okay? And if the 50 kilogram object was replaced with a 100 kilogram object, how would the intensity little g change? Well, if you go to the equation in the left box here, you might be tempted to say it would go down by a factor of 2, because in this case we have twice the mass. However, you got to realize up in the numerator would also be twice the force, so they'd cancel out. So when you ask how does little g change based on factors, again, go with the second equation. The mass of the little object is not in there. This is the source of the field right here, not the object in the field, feeling the force. So there'd be no change. That's the hard thing for kids to realize. Okay? How would the force of gravity, in other words, the weight change? Well, if we have twice the mass, okay, then from this equation right here, this stayed the same, this goes up by a factor of 2, therefore the force of gravity would be 2 times greater. Okay, and so this graph right here just shows you how little g changes with the distance from the center of the Earth. Okay, so right about here is at the surface of the Earth, and it drops off very, very quickly by the square of the distance as you go further and further away. And if you go inside the Earth, it grows rather quickly. Okay, so that's the end of our introduction to the idea of universal gravitation. We'll talk more about these G and GFI problems in class.